Okay, so back to the quantum mechanical view of the atom. I said at the end of the last video that one of the most important things that we need to understand before we get too deep into quantum mechanics is something that's called the wave function. And so if we think of a wave, and the waves that you are more familiar with would be like electromagnetic waves more than particle waves. But any wave, both electromagnetic and particle, really have three important properties: their wavelength, their frequency, and their amplitude. So for electromagnetic waves like light, the wavelength is what tells us if the light is visible or not, and if it is visible, what color it is. The frequency tells us about the energy that the photon is carrying. Remember, EP equals HF. And the amplitude tells us about the brightness or the intensity of the light. Okay? And so for electromagnetic waves, these three are pretty straightforward. So now the quantum mechanical view of the atom is really looking more at particles. So for particles, we know the wavelength, de Broglie's wavelength, is connected to the momentum. Remember, lambda is equal to h over mv, but we also know that momentum is equal to, I guess here, this is the momentum. So it relates, I was going to say mv, but I didn't really need to write it. So it relates the wavelength to the momentum for a particle wave. And and frequency then would be connected to wavelength. But it's the amplitude that we need to look at. And it's the amplitude that we call the wave function. Okay? So the amplitude is this psi. And what we know is that it is dependent upon both the particle's position and the time. So it's a function of position and time. Okay? And it's like, where is the particle at any given moment? Right? So if you imagine, here's the wave, like the particle is moving in a wave form. So like, where in the wave is the particle at any given moment? And because depending on where it is, that will determine its amplitude. Okay? And really, calculating the wave function at any given moment in time is one of the fundamental tasks of quantum mechanics. And so going back to Heisenberg and Pauli and all of those guys, they were trying to figure this out. Like, so this electron that's inside the atom, where is it? And trying to determine where it was became a very difficult task, because the act of trying to see where it was screwed up and changed where it was. But I'm jumping ahead of myself. First, before I go there, I want to talk just for a minute about Schrodinger. And a number of you had Schrodinger as you're due to do research on, and we'll talk a bit more about him as we go on here. But Schrodinger's wave equation is something that's pretty famous, and there's about 3 different versions of Schrodinger's wave equation. The one I'm going to show you is the one that's based just on position. So we said a minute ago the wave function is a function of both position and time, and Schrodinger has his equations for both of those, but this one is just for position. So energy, the wave function with respect to position, is equal to, and you're going to love this, Planck's constant divided by 2 pi, which is what the h bar means, divided by 2 pi, and that's squared, over 2 times the mass of the electron. And then I don't know if you got far enough in calc, those of you in calc, to know what this is yet, but maybe. This is the second derivative with respect to position of the wave function, plus the potential energy with respect to position times the wave function again. So this is Schrodinger's wave equation, which he figured out to try to determine where is an electron at any given moment in an atom with respect to position. Okay? Now, the problem, it's not relativistically correct. It doesn't hold up at speeds close to the speed of light, which is where Einstein began to get antsy towards the end. So Einstein contributed to this model, but later in life he was like, but there's something wrong, and he could never really bring everything together to his satisfaction. Okay? But from this equation, this Schrodinger's equation, the solution of this equation, or the solution for all the energies of all the electrons in an atom can be found. So you can figure out the energy that every electron in an atom can have from this wave equation. And so it becomes the foundation for all of chemistry. Okay? This and the others. Now, obviously, I can't give you any homework questions with this equation because the majority of you don't know what second derivatives are yet. Like, we wouldn't solve this. And remember that book I showed you earlier in the semester that was called Quantum Mechanics Demystified? Even demystified is still above your pay grade at the moment. But I just wanted to show you that, like, this isn't child's play stuff. I have 4 courses in quantum mechanics. My second year of university, I took quantum mechanics 1, my third year quantum mechanics 2, my fourth year quantum mechanics 3, and then in my master's I did advanced quantum mechanics. We are going to do like a week on quantum mechanics. It will not be the end of the story, the full picture, or anywhere close. But it'll be enough to give you a taste for what it is, and a taste for the fact that it can be a little mind-bending at times, because it kind of means that everything we thought we knew, we don't really know, because things are not as it seems. Okay, so just hold on here. All right, so back to this wave equation and back to our wave function. Okay, so you can think of our wave function of psi just as the amplitude of our matter wave, of our electron, at any point in space and time. Okay? Now, the problem is finding it is next to impossible. And it's the task that a lot of them were doing. And we're going to get in a moment to the point of realizing that we can never actually find this wave function. The best we can find is the wave function squared. And this part is brought to us by Max Born, another one of the scientists that some of you would have had. Max Born is the one that realizes that the best that we can find is the probability of an electron being at any given point in a certain period of time. So the best that we can know is the probability of this. Okay, so it tells us the probability of where an electron would be. And if in grade 11 you did the different shapes of like the n equals 1 and n equals 2, really those shapes are the probability. They're the high, like the denser the cloud, the higher the probability. The less dense the cloud, the lower the probability. Okay, so it's the wave function squared that will give us the probability. This is connecting us to Heisenberg's uncertainty principle and all of that. But first I need to tell you about someone who's called Dr. Quantum. Or maybe it's Professor Quantum. I'll have to double check before the next video. Anyway, he's like a superhero in the physics thing. And he talks about the double slit experiment, which in grade 11 physics we did when, you remember, we had 2 slits and we put water and we talked about light going through and it came out the other side and they interfered with each other. And on the back line, we got bright spots and dark spots. Okay, so I'm going to put up a video clip of Dr. Quantum because or Professor Quantum